Okay, so the next very important thing that we're going to take a look at, and this is maybe the most common thread throughout every chemistry class that you will ever and have ever taken, is this idea of stoichiometry. Okay, and stoichiometry is predicated upon having, and this is super critical, is having a balanced chemical equation, right? So we talked previously about making sure that the equations are balanced, and this is one of the reasons why, is because you cannot do stoichiometry without having that balanced equation, right? So that's why it's really, really important. And this is at the heart of pretty much everything that any calculation that you're going to do in chemistry, is usually going to have some sort of stoichiometric component to it. So another example of where we have a big fancy word, stoichiometry, that really means something very simple. So let's take a look at an example of an equation, very simple equation. We've seen this one before, um, to illustrate and to remind ourselves about what stoichiometry actually is, right? So we have the combination reaction of nitrogen and hydrogen reacting together to produce ammonia, and then we're going to balance this equation. So we put a 2 in front of the NH3, we need a 3 in front of the H2, and then we have a 1 here. We don't need to put the 1 in, but it's understood, in front of the N2. So when you think about your balanced equation, really what this is giving you, and in addition to it being a chemical sentence, you can think of it as sort of a recipe for making, in this case, ammonia, NH3. So what this says literally is that one molecule of nitrogen gas, N2, reacts with 3 molecules of H2 to produce 2 molecules of NH3, of ammonia, right? That's literally what the balanced equation is telling you. So we can get a recipe for making ammonia in this case. So if I need to make 2 molecules of ammonia, I know that I need exactly 1 molecule of N2 and 3 molecules, well, of H2. Well, it is often impossible to work with individual molecules because they are incredibly tiny and incredibly small. So realistically, what we do is instead of working with molecules, we use moles. So we can also say 1 mole of N2 reacts with 3 moles of H2 to produce 2 moles of NH3. And this is more realistic because moles, remember, represents Avogadro's number of things, which is 6.02 times 10 to the 23. And that's more realistic in terms of the amounts that we can measure out in the lab. The key thing here, though, that's common to both of these interpretations of this equation is the coefficients, right? So we have the 1, the 3, and the 2. 1 mole of N2, 3 moles of H2, 2 moles of NH3. And that is really at the heart of every stoichiometry problem. Okay, so those coefficients that we use to balance the equation, and this is the key thing now, they give a mole-to-mole ratio. And that mole-to-mole ratio is at the heart of every stoichiometric calculation. Okay, this is the most important thing. This is what allows you to connect anything in an equation with any other thing in that same equation, is that mole-to-mole ratio. So how is that useful? Well, we can say, just by looking at this equation, we can say 1 mole of N2, and we can use that ratio to set it up as a conversion factor. 1 mole of N2 for every 3 moles of H2. Okay, or I can flip it. 3 moles of H2 for every 1 mole of N2, right? All I'm doing there is using the coefficients from the balanced equation to write these mole-to-mole ratios, which can be expressed as conversion factors. I can relate any two things in that equation. I can relate the H2 to the NH3. I can say 3 moles of H2. I can put that over the 2 moles of NH3, or I can flip it. I can say 2 moles of NH3 for every 3 moles of H2, right? So there's nothing groundbreaking here. All you're doing is just use, and the equation needs to be balanced. That's really the groundbreaking thing, is that when your equation is balanced, all you're doing is using those mole to mole ratios, okay? And that allows you to convert from one thing to any other thing in that equation. That's the main bridge. Let's take a look at an example. So if you start with 7.5 moles of N2, how many moles of H2 would be needed to react completely? Okay, so and all of these problems that you're going to face, and you've seen this before, half the battle is just trying to figure out what is the question actually asking you to do. Okay, and that's where your reading comprehension is going to be super important. All this is asking you to do is to relate N2, moles of N2, to moles of H2, right? Those are the two things that you want to relate together. So looking at my equation, there's my N2 and there's my H2. I'm not concerned about the NH3 at this point because it's not relevant. So what's the relationship between the N2 and the H2? Well, we already wrote that down over here. It's a 3-to-1 ratio or a 1-to-3 ratio. Okay, it's not that complicated. Now you're told what you're starting with, the 7.5 moles of N2. So if I start with you always start with what's given. So if I start with 7.5 moles of N2, okay, put that over 1. And if I want to end up with moles of H2 as my final unit, guess what? I'm going to pick the conversion factor that has the moles of H2 on top. So 3 moles of H2 for every 1 mole of N2. Moles of N2 goes away. This is where your dimensional analysis skills are going to be useful. Some of you could probably do that in your head, and that's fine. The point here is to remind you, because I know you've all seen this before, is of the strategy for using these multiple ratios when it comes to stoichiometry. So 7.5 times 3, whatever that gives. So we get 5 there. That's 15. That's 22.5 moles of H2. Okay, so your multimole ratio from the balanced equation allows you to convert moles of one thing to moles of any other thing in that equation. Well, how often do we actually use moles? Do we measure out moles in the lab, or do we measure out masses, for example, in the lab, right? And the answer to that is we usually measure out masses of things or volumes of things. So how do we get from mass of one thing in an equation to mass of the other thing? Well, we're still going to use the balanced equation, but now we're going to use another thing that you would have seen before. So if I take a look at mass to mass stoichiometry now, so we looked at that's mole to mole stoichiometry above. So mass stoichiometry is going to be the same idea with 1 or 2 additional steps. So for example, if you start with 7.5 grams instead of moles, 7.5 grams of N2, how many grams of H2 would be needed? Okay, so now I want to get from grams of one thing to grams of the other thing. Well, the equation, the balanced equation, doesn't give you a gram to gram relationship. It doesn't give you a mass to mass relationship. It gives you a mole to mole relationship, right? Which we've used before. But we're given grams. So how, in order to use the equation, we have to get to moles, right? So that's the key thing when it comes to every stoichiometry problem, get to moles. Okay, because then the whole equation opens up. So can you convert grams of something to moles of that thing? And the answer is yes, we can convert grams to moles using the molar mass of that substance. And as long as you have a periodic table, you can calculate the molar mass of something. Okay, so for N2, okay, we have 2 nitrogens in here. So 2 nitrogen is 14.01. So this is 28.01 grams. This is a 1. Of N2 is 1 mole of N2. The other thing that we need to do this is the molar mass of the H2. So H2 here, we have 2 hydrogens. Okay, hydrogen is 1 point, well, you go to 2 decimal places, 1.01, so this is 2.02. Sorry, I did a miscalculation. It should be 28.02 above. And then 2.02 grams of H2 is 1 mole of H2, right? So these are equalities again for molar masses that we can use as conversion factors to convert whatever it is that we needed to. So when we do this calculation, again, starting with what's given, okay, so I have my 7.5 grams of nitrogen, so that goes first. I want to first of all get to moles, right? So because then I can use my mole to mole ratio. So I'm going to use this first conversion factor, this first equality. I want to end up with moles, so my grams go on the bottom, 28.02 grams of nitrogen for every 1 mole of N2, right? Molar mass gets me to moles because grams cancel. Then I'm not going to put equal. I'm going to incorporate my other conversions. I want to get to now, I'm sorry, right now I'm at moles of nitrogen. I want to get to moles of hydrogen. I'm going to use my mole to mole ratio that I've used above. So 3 moles of H2 for every 1 mole of N2, right? And this comes from the balance equation. Moles of N2 goes away. I'm at moles of hydrogen. Now I want to get to grams of hydrogen. I'm going to use my molar mass, stick that in there as the last conversion factor. 1 mole of H2 is 2.02 grams. Put the grams on top because that's the unit that I want to end up with. And the only unit I am left with is the grams of H2. Okay, I can just go ahead and use your calculator and do that calculation. So that's mass stoichiometry in a nutshell. For any stoichiometry problem you're doing, you have to get to moles, right? That's probably the most important thing. Not probably, it is the most important thing that you have to do when it comes to stoichiometry. Convert whatever you're starting with to moles, first of all, then you can use your mole to mole ratio to connect one thing to something else in that equation.